Um, our next lecture will be given by Professor Prem from Nanyang Technological University, Singapore. Professor Prem had a long time experience in spintronics and magnetism for more than 30 years. And his expertise is in magnetic nanostructures, magnetic recording, and spintronic materials. And his current research focuses on neuromorphic computing and also magnetic recording. So he's going to talk about brain-inspired computing based on domain-wide devices for today's lecture. So let's welcome Professor Prem.
Thank you for the introduction and also thanks for inviting me. Good morning, everyone. So this is my sixth real talk. So based on where I go and depending on the audience, I'm trying to fine-tune the presentation to suit the audience. So here I understand that you are from different backgrounds, so I'll spend more time on the introduction, and if you are more interested in the topics that we do, you can always approach me or the students for detailed questions. So this talk will be on brain-inspired computing, and we are just after the coffee break. So until all the audience come in, I'll spend some time in doing commercials. Okay, so the first one is about IEEE 90 Society. Our president has already spoken a lot about the IEEE 90 Society. So I'll skip this slide, yeah, spend some time to acknowledge our funding agencies. So I have a PRP grant of about $6 million to research on neuromorphic computing. So I'd like to thank our funding agency, which is the National Research Foundation of Singapore. Then we also are funded by A-Star of Singapore. And this work was done by many of my students and postdocs listed here. And we also have been collaborating with the A-Star of Singapore, Sultan Qaboos University, Professor Sbia from this university, then Global Foundries Singapore, and also IIT India. So quite often people don't know where Singapore is. Actually 25 years ago when I wanted to go to Singapore, I also tried to find a map and I found it very difficult. So yeah, this is Asia, Taiwan somewhere here. So Singapore is somewhere here below Malaysia. It's connected by a bridge which is like 1 kilometer long. So we call Singapore as a little red dot because if you place a dot to represent Singapore in the world map, the dot will hide Singapore. So that is the size of Singapore. It's around 600 square kilometers. And NTU is located at the western side of Singapore. So NTU has a strength of 2,000 students, and we are located in an area of 200 hectares. And it's quite a green campus. And we also are always concerned about energy. So we are fully going with solar cells. All the roofs of NTU buildings are covered with solar cells. And we are going to be in the self-reliant mode. And the NTU is a full-fledged university. So we have engineering faculty, science faculty, social sciences, medicine, business, and so on. So my lab is called the Spin Lab. So here N is capital because N stands for nanostructures of neuromorphic computing. And we are using spintronics to do neuromorphic computing and nanostructures. So we have a few sputtering machines, a few lithography machines, ion beam capability, and we have equipment to characterize the electrical and magnetic transport measurement. So we can do most of the studies within our lab. So I tell my students that if you want to publish an APL paper, you can do everything within our lab. But if you want to go for science or nature, you have to collaborate with other people. So that's the status of our lab. Okay, so I want to make this talk interactive. So I'll ask some questions via this app called MOOC Lab. So I suggest all of you to scan this QR code, and when the question comes, yeah, please answer the questions. The questions are rapid fire type, so you have to be on your toes, so you will get like 10 to 15 seconds, so please answer quickly, and the winner will show the name. Okay, so if you enter your name and you are the winner, probably your name will appear here. Okay. So have you all scanned? So even if you haven't scanned later, this link will appear. You can type this link in your browser, then answer the questions. Okay, the first question is very simple. So I can see how many have answered. And sometimes, suppose this is the right answer, and there is a distribution. That means the concept that I'm explaining is not clear. So this also gives me some idea of whether I'm going in the right direction or if I have to do some course correction. Okay? So this always helps me to teach. Okay, so this is the outline of my presentation. So I'll spend more time on the introduction, then we'll discuss the fundamentals. Then I'll explain how we can design neurons and synapses for neuromorphic computing using spintronics. Then I'll discuss some of our work on synapses and neurons. Then I'll end my presentation. So this will be the flow. Okay, so here comes the first real question. Yeah, as I said, this is a rapid fire question. You have to be on your toes. Okay, most of you have used very strange, somebody, I think they pressed the button probably.
I want to talk to the person who said no.
I saw you using ChatGPT yesterday.
Please, the person who said no, come see me after.
So we have been using artificial intelligence for many years, and if we haven't used any of this application, at least as I saw from the previous question, we have been using artificial intelligence. So here AI is artificial intelligence, not the Apple intelligence that just came yesterday or 2 days ago. So we have been using ChatGPT and so on. In addition to all these applications for common people, artificial intelligence also has been useful for researchers. For example, it takes 5 years to crack the structure of a protein because people do X-ray crystallography, and it takes 5 years of a PhD student to crack the structure of one protein. Okay? But with artificial intelligence, now people have understood 200 million proteins. Okay? That means 1 billion years of PhD time is saved. So these are some of the applications of artificial intelligence. And artificial intelligence is typically carried out using neural networks. So we have a network of neurons and the synapses or waves. So the neurons are connected to each other. So we have the input neuron, then we have the output neuron. Then based on the network, you can get your answer correctly. And depending on the complexity of the circuit, you may have several neurons and many layers. So in ChatGPT, for example, there are 100 trillion connections. So if you look at the structure, the neurons are connected to each other. So if you have several layers, several neurons, the connections are very enormous in number, and because of this, lots of data flow back and forth between neurons. So if you are using the current architecture, which is the von Neumann architecture, which was proposed 7 decades ago, then we have a problem because the processing is carried out here and the data is stored here. So during all the operations that we do, the data has to go back and forth between the CPU as well as and the memory unit. So to give you some numbers, if you take a personal computer, the spacing between the CPU and memory is like 4 centimeters. So if you consider a 40 nanometer transistor inside your CPU, So that 4 centimeter compared to the 40 nanometer, it's like one human going 1,000 kilometer to get something and coming back. Okay, so that is the kind of distances we are talking about. So that causes delay and power consumption. So it's very clear that the existing hardware and the algorithms that we use for artificial intelligence consume too much power. Okay, so because of this problem, people are trying to get inspiration from the brain. So we know that a few years ago, a supercomputer beat human by playing the game Go. Okay, but if you look at the supercomputers, I mean, they may be able to perform operations faster than human brain. But if you compute the efficiency of a human brain, for what human brain can do more operations than a supercomputer. So there is a huge energy saving potential if we look at the brain and get inspiration from the brain. So that is the idea behind neuromorphic computing. So basically, neuromorphic computing means that we are deriving inspiration from brain and coming up with new hardware elements and new algorithms to achieve energy efficient intelligence computing. So that is the topic that we are going to discuss. And I will be focusing more on the hardware elements which are useful for neuromorphic computing. Okay, so now we move on to discuss the fundamentals. So people don't know exactly how the brain works, but they know that brains have neurons, synapses, and the neurons fire, and the signals go from neuron to other neurons through this axon, which are like the connecting cables, and there are synapses. So neurons are like the processors of the brain, and the synapses, or the synaptic elements that you see here, they are the elements that store the information. So they are like the memory. So let's spend some more time to understand what the neurons and the synapses are. So to understand neuron, you can consider a water tank as an analogy. So this particular water tank has many inlets. So if the water is coming through various inlets, then this tank will be filled quickly. And when the water level reaches certain level, so this part will act like a siphon. So the water will be completely drained out. So in a similar sense, we have neuron. So neuron can receive inputs from many other neurons. And when so integration of the inputs is like the water tank getting filled up because of the flow of water from different inlets. So the neuron will receive the inputs, and when the signal it received exceeds a certain threshold, the neuron will get excited, it will produce an output, then it will go back to the ground state. Like the water goes out of this through the siphon effect and the water level becomes empty. So similarly, the neuron will go back to the ground state. So that's how the neuron function. I think I'll play a video to understand this more visually.
I need to think about two things. How hairy was the animal in the picture, and how big was the animal in the picture? I want you to think about those things in terms of like a scale of 1 to 10 while I explain what's going on over here, okay? So we've got these two containers that we can pour water into through these funnels. You can think of these like neurons. So this needs to be able to identify if something is hairy or not. This needs to be able to identify whether an animal is big or not. We'll start with hairiness. Question 1, on a scale of 1 to 10, how hairy was the animal in the picture I showed you?
I think about an 8.
About an 8, okay. So we've got all these beakers of water here that they're labelled 1 to 10. And you can see the amount of water goes up as the number goes up. So you chose 8, right? There we go, so that's quite a lot of water. So take that, and I want you to pour that into the funnel. Can you reach that? Yeah, just about, okay, great. Yeah, keep going, that's fantastic. So because you chose quite a lot of water, the level should be able to rise to at least this funny little U-bend here. I want you to watch what happens when it gets there. Look at that. So that channel has now turned into a siphon, and that siphon effect.
So basically this is a two neuron computing unit. So here they are doing computation using just two neuron, two input neuron and one output neuron. And you saw the siphon effect. So when the water level gets filled above certain height, it gets drained out. Okay. So this is exactly the neuron function. But one difference, if you have noticed, that in the previous image I showed a hole that will leak water. Okay. So in this example that you saw, there is no leakage function.
Just going to see.
So basically, when we design electronic counterpart of a neuron, we have to consider all these effects. So the electronic neuron should be able to receive electrical inputs from many other neurons in an analog-like manner. So it should integrate the signal and it should also leak the signal. For example, here I have plotted some physical property X. So when there is a signal shown by this orange color pulse. So when there is a signal, the X changes, and when there is no signal, the property leaks and it comes back to the ground state, and when there is another signal, it goes up, and when there is no signal, it goes down. So this part is called leaking function, and this part of signal, something going up, is called integrate. And when the neuron reaches certain threshold, it should fire. Okay, for example, here the threshold potential is reached, so the neuron fires and comes back to the ground state. So this is what we expect when we design a neuron, and which will roughly resemble how a biological neuron works. And when we talk about synapses are the connection between two neurons, and they are called waves in neural network, and they help to remember the information. Okay? And the synaptic strength gets stronger and stronger as you keep learning. So to give you some analogy, let's say you are in a cliff somewhere here outside this slide, and you want to go to this cliff. Okay? So it's very far. I mean, you cannot climb down and climb up. That's very difficult. So what you may do is you may throw a rope, tie it here. Okay, then with some difficulty, you may hold the rope, then cross. Okay? So if your rope is long enough, when you are coming back again, you may throw another rope. Then now the path has two ropes, so maybe it makes your job easier to go from here. Okay? But as you keep going back and forth, you can even build a bridge using your rope. Then you can easily walk. Okay? So that's how the brain works. So when we learn some concept for the first time, the synaptic connections are weak. So we find it difficulty to learn. But as we learn repeatedly, suppose it's mathematics, you do calculation repeatedly, it becomes easier. So that's how the brain works. So the synaptic connection becomes stronger and stronger as you learn. So when we design electrical analog of synapses, what we are looking at is, we are looking at some device whose resistance can be varied as the learning progresses. So maybe initially the resistance between two neurons is higher, but as the learning is established, the resistance may go down in value. So we need a device whose resistance can be varied by electrical means. So that's what we need. So when we look at synaptic devices, we are not looking at a device that just stores 1 or 0 state. We want the device to store multiple values of resistances. So this property is exhibited by many different types of material candidates. So resistive random access memory, or ferroelectric materials, space-change materials, all show this phenomenon of variable resistance by electrical means. But for this talk, I'll be focusing on spintronic domain wall devices. whose resistance can be changed by electrical means. Okay, let's do some question. So this is a time to recap, reinforce the concept. Okay, all right. Very good. Next question. The majority of you are right. You understood that neurons are like processors and synapses are like memory elements and axons are like the connection between different neurons. Okay. These are the okay, so some more fundamentals. So when we talk about magnetic materials and magnetization reversal mechanism, so people always talk about domain wall motion. Okay, so magnetization reversal by domain wall motion is one type of reversal mechanism. There is also another more important reversal mechanism which is called coherent rotation or Stoner-Wohlforth reversal mechanism. So Stoner-Wohlforth reversal mechanism or coherent rotation is commonly more useful in the high-tech. Okay. So if you take hard disk drives or MRAM, so there we are using single domain structures which reverse the magnetization in a coherent rotation manner. So hard disk media, MRAM are based on coherent rotation reversal mechanism. However, some other materials, I mean most common materials undergo the domain wall motion mechanism. So when you apply a magnetic field, maybe one particular domain is favored and this domain expands, and this is called domain wall motion. So in the case of, if you ask me which kind of materials show domain wall motion or which kind of materials will show coherent rotation, commonly if you go to a lab, you sputter a thin film sample, most of the thin films that you deposit will form this kind of domain wall motion. But if you have some special care, if you segregate the grains with some spacing between each other, or if you do lithography and get nanostructures, then you will have coherent rotation. Okay. So MRAM basically uses single domain structures, and MRAM uses something called magnetic tunnel junction. So in the magnetic tunnel junction, you have two ferromagnetic layers separated by an insulating layer. So here I mean this slide is from Professor Stuart-Parkin, and here we have color-coded the two ferromagnetic layers. So if they have same color, that means the magnetization direction are the same, and if they have different color, the magnetization direction are different. So when the magnetization direction of the two ferromagnetic layers are the same, then the electrons have larger probability to tunnel from one layer to the other layer. So in this case, the resistance will be lower, and if they have anti-parallel magnetization, the probability for electrons to tunnel from one side to the other is lower, so they will have higher resistance. So this property is what is used in the magnetic random access memory. So this stores only 0 or 1. So to the students who are not very familiar with the MTJ, I always give Oreo cookie as an example for magnetic tunnel junction, because the thickness of this and the diameter are more or less very similar to the MTJs that we use in the MRAM. So this corresponds to a ferromagnetic layer, this is another ferromagnetic layer, and this is a magnesium oxide barrier. Okay? But this is not suitable for the synaptic application that we are going to discuss. So I mentioned that for synaptic application, we need some device it should show not just a 0 and 1, but it should have multiple resistive states. So in that sense, domain wall device that we proposed like 10 years ago will come into use. Okay, so here again, okay, maybe to digress a bit, this is an example where we are using the domain wall motion to make a very practical devices. So racetrack memory is based on the domain wall motion to make high-tech devices. So this concept was derived from here. But we have this kind of ribbon-like magnetic terminal junction to achieve multiple resistance state for multiple cells, multiple bits per cell. So this is the concept that we proposed like 10 years ago. At that time, we were not aware of neuromorphic computing, but we realized that this could be useful for neuromorphic computing. So for the MRAM, I gave you the example of Oreo cookie. Then if you ask me what is the shape of this is like KitKat. Okay, so in KitKat you have like a long device, so you have layers. So that's the kind of domain wall device we are looking at. So in this case, you have again two ferromagnetic layers. So you have one reference layer and one free layer. So here you can create a reverse domain, and you can move the domain wall from this side to the other side. So depending on how much of the magnetization is parallel or anti-parallel, you can have multiple resistance state. So this is the concept of domain wall devices, and they will be used in synaptic application. Okay, so now I move on to the third part of how we can use this spin-based neurons and synapses for neuromorphic computing. Yes.
So for these, domain wall devices, which type of magnetic anisotropy is preferable, in plane or out of plane?
We are looking at perpendicular anisotropy.
Okay.
Because the domain wall can be narrower in perpendicular magnetic anisotropy.
Okay.
Okay, thanks. So about 5-6 years ago, researchers from Purdue University, they proposed a neuromorphic computing circuit based on the domain wall devices that I just showed in the previous image. So you can prepare a crossbar array of neurons and synapses, and this kind of circuit can perform neuromorphic computing architecture. And this slide is a bit crowded, so I move on to a slide with a clear description of neurons and synapses. So you can actually create various types of neurons using the magnetic tunnel junction based domain wall devices. So in this slide I show two types of neuron. One is step neuron, another one is called spike neuron. So in the case of step neuron, you have the reference layer and the free layer throughout your device. So your whole KitKat is having both the reference layer as well as the free layer, and the domain wall position changes results in a change in the output that's almost linear or something like that. Whereas in the case of second neuron called spike neuron, you have the MTJ type of thing only on the right side. So we have a barrier layer, we have a reference layer, and this is the free layer. So free layer is empty for most part,